Okay, this is chapter 6, probability, and this specifically is conditional probability and independence. If you look, it says in this section you should be able to calculate and interpret conditional probabilities, use the general multiplication rule, use tree diagrams, determine if two events are independent. We've talked about mutually exclusive, but independent is something different. And then when appropriate, we're going to use the multiplication rule for independent events. If you'll turn to the back, we'll start on here. It says, what is conditional probability? It is the probability that we assign to an event can change if we know that another event has occurred. So conditional probability depends on a condition, and a condition is that an event has already occurred. This idea is key to many applications of probability. When you're trying to find the probability that one event will happen under the condition that another event is already known to have occurred, you're trying to determine a conditional probability. So there are examples here. Now, they use it with A and B. So for instance, in here it says, suppose we know that event A has happened, then the probability that event B happens given that event A has happened is noted by this. So this is the way you'll see it written in your textbook or on your test or exam. It says P parentheses B slash A, and that's read as probability of B given that A has happened. So that's how you read it. Probability of B given that A has already occurred. So here's what the formula actually looks like. It is the probability of A and B over the probability of B. If you notice, if you're given that B has already occurred, that automatically makes probability of B your denominator. This is the probability of B given that A has occurred. So this automatically makes the probability of A your denominator. So what we like to say is what you are given is your denominator. So you won't always be dividing by 1, you'll actually be dividing by the probability that you're given as we go into these examples. So if you'll turn to page 5, I'll get that out of the way. It says calculating some conditional probabilities, and in this one, let me focus it. It says that there are two events. Event E is that the grade comes from an EPS course, and event L is that the grade is lower than a B. So the first thing we asked to find here, and there's your table. First thing we're asked to find is the probability that L happens. Well, L is the grade is lower than a B. So if we look for how many grades are lower than a B, that would be 3,656 grades that are lower than B. Out of the total number of grades, which are 10,000, we divide the two and we get 0.3656. And that's just basic probability, no conditions there. Now, in the second one, you are finding the probability of E, and remember this is given. That's the line means given that L has already happened. So L is what has already occurred. So L is the grade is lower than a B. So we know, or we are given, that their grade is lower than a B. So that is our denominator because we are given that. So we're only looking at the 3,656, and we want to find the probability that E happens, so that the grade comes from an EPS course. That would be engineering and physical science. So again, we can only look in the below B area because we're given that that happens, and so that is 800 out of 3,656, which is 0.2188. Okay, the last one says find the probability that L occurs given that E has already happened. So we know that E has happened. That is, the grade comes from an EPS course, so we're given that. So that means we are only looking at those 1,600 students. And we want to find the probability that their grade is lower than a B. So in those 1,600, how many have a grade lower than a B? There's 800 of those, and so 800 divided by 1,600 is 50%. So remember, the given, if we're not given anything, it's the entire total. And then whatever we're given, which in this case was that the grade's lower than a B, we look at that total. And this one we're given that the grade comes from an EPS course, so we look at that total. So what we're given is your denominator, which is in turn what you're dividing by in the conditional probabilities. Okay, this is a general multiplication rule, and it just says the probability that events A and B both occur can be found by using the general multiplication rule. The probability that A and B occurs is the probability of A times the probability of B given A. Now all that means, that seems a little tricky, but all that means is the probability of A happening times the probability of B happening, given that A has already happened. Well, we already said that A happened here, so this is really just A times B. So if you look in words, this rule says that for both of two events to occur, the first one must occur, and then given that the first event has already occurred, then the second must occur. So for instance on that would be like if you want to flip two coins and land on tails, there would be a 50% probability for the first one to occur, and then given that that's happened, there would then be a 50% probability for the second one to occur. So to get both to occur, you would have 0.5 times 0.5, which is 0.25, and that would be the probability of getting two tails from two flips of a coin. So if you'll flip over to the tree diagrams, this is number 7. Speaking of the coin, it says the general multiplication rule is especially useful when a chance process involves a sequence of outcomes, and we can use a tree diagram to display the sample space. So we're going to look at actually flipping a coin twice. What is the probabilities here? So the possible things that could happen, those are your sample space. You could flip a coin and it land on heads twice. You could flip a coin and it land on heads the first time, tails the second time. It could land on tails the first time and then heads the second time. Or it could land on tails twice. So there's 4 possibilities. So again, the probability of getting 2 heads on 2 tosses of a coin is just 1 out of 4. Now, looking at that from a tree diagram standpoint, you see you toss a coin and there's 2 options, heads or tails. 50% chance on each. They put 1/2, you could have put 0.5. That means the same thing. And then after you've tossed the coin, now that you know it's landed on heads, the second one has 2 options, which are also 50% on each. Now if you toss the coin on tails, then the second toss again has either heads or tails, and they both have 50% chance of occurring. Now to find the total probabilities, you multiply them. So for heads and heads, it's 0.5 times 0.5. For heads and then a tail, it's 0.5 times 0.5. For tails and heads, 0.5 times 0.5. And for tails and tails, same thing. So each one of them has a 0.25 chance of occurring, or a 1/4 chance of occurring. And that's a tree diagram for toss of 2 coins. And down below, here's another tree diagram, a little more complex than the 2 coins. But this one says the Pew Internet and American Life Project found 93% of teenagers use the internet, and 55% of online teenagers have posted a profile on a social networking site. So we want to draw that in a tree diagram. So first of all, we would randomly select a teenager. So it looks back to kind of how you set up an experiment. That's what these tree diagrams kind of look like. Now 93% are online, so 0.93 are online. It's said in the problem, which means 7% are not online. So that's what we have in our first column here. Now in the second 2 branches, if they are online, okay, then 55% of those have created a profile on a social networking site, which would mean 45% of those have not created a profile on a social networking site. If they are not online, then their chance of creating a profile is 0, because they will not create a profile since they are not online, and their chance of not creating a profile and not being online, that's 1 right there. Okay, so to find the actual probabilities, the probability of being online and creating a profile is 0.93 times 0.55, which is 0.5115. And what that tells you is a little over 51% of teens are online and have posted a profile. We can also see that 0.93 times 0.45 would tell us how many are online and have not posted a profile. 0.07 times 0 would tell us how many are not online and have posted a profile, which is none. And 0.07 times 1 would tell us how many people are not online and have not posted a profile. So those are the tree diagram, and again, to get the probabilities at the end of a tree diagram, you're actually multiplying the two together. Alright, go to the next page. This is the third and last one. It says what is conditional probability. Probability we assign to an event can change if we know that some other event has occurred. This idea is key to many applications of probability. So when we're trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we are trying to determine a conditional probability. So anytime we talk about conditional probability, that's why I've underlined this. It means because you know that an event has already occurred and you want to try to see what the chance of another one happening given that that one has occurred is. So the probability that one event happens given that another one has occurred is conditional probability. And again, we had already spoken about this and went through this earlier. So let me flip to the next page. And I think the last one, the multiplication rule, and hopefully you see here when we talk about the multiplication rule, following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was measured that the probability that an individual O-ring would function properly was 0.977. So we assume that they succeed or fail independently. Now, if we assume that they are independent events, then probability of A times probability of B is how we can find them. So assuming that they fail independently means we can just multiply their probabilities. So each of them had a 0.977 chance of working okay. So the probability of all 6 working okay was multiplying those 6 numbers together and getting 0.87, which meant there was an 87% chance that the shuttle would launch safely. And also that would mean there's a 13% chance that it wouldn't launch safely. Now, the only way we knew these were independent was from the problem. So the problem told us it was independent, which meant that we can actually multiply them together to get their probability of all happening. So for all of them to function okay, we multiplied them all together to see. So a little summary in here. Remember, conditional probabilities, you can see how you would do those and some of the different formulas they have there. You're going to use the general multiplication rule, so don't forget about that. A times B there. You're going to have to be able to use tree diagrams. You have to be able to determine if 2 events are independent, and we'll talk about that more as we get into tomorrow's class. Tomorrow goes through more of the independent, and then when appropriate you're going to have to use the multiplication rule for independent events, and that was just what we did in the last problem with the space shuttle. So now you go back to the multiple choice problems from earlier today. What I like for you to do is get those out. I said test 5B at the top. Those were multiple choice, and what you're going to do is put number correct in a line there, and you just want to see how many of these you got correct. So if you'll switch with a neighbor, we'll go through them real quickly and you want to see how many you got correct out of 10, and we'll see about adding points for the test there. Okay, number 1. A fair coin is tossed 4 times, and each time the coin lands heads up. If the coin is then tossed 1,996 more times, how many heads are most likely to appear in these 1,996 tosses? Okay, well, what you need to know is that each toss is independent of the other, which means it doesn't affect the other. If you get 100 tails in a row, still a 50% chance of heads the next time. So in 1,996 tosses, half of them should still come up heads. That's how many we expect to appear, and that's 998. Okay. Remember, future behavior is not affected by past behavior, so none of this matters. All that matters is if the coin is tossed 1,996 times, how many do we expect to be heads? And that is half, which is 998. In the second problem, which of the following could be the model? The only choice is B, because a probability model must add up to 1. So look at all these. None of these add up to 1 except for B. And if you add these probabilities, they all add up to 1 in B, and that's what it has to do. Number 3, it says you select one musician from this group. What's the probability that they play a woodwind? So we look at woodwinds. There's 14 out of the total number of people in the group. That's 88. That gives you C. You select one musician from the group at random. If the person is a male, what's the probability he plays a woodwind? So we know the person is a male. So we're given that they're a male. There's only 44 of those. And how many males play woodwind? There's 8. So 8 out of 44. Okay, flip to the next page. Number 5. You select one musician from the group. It says at random, which of the following statements is true about the events plays a woodwind and male. So the events are not mutually exclusive, meaning that somebody can play a woodwind and be male, because 8 of them do. So any that said they are mutually exclusive, we would have to mark out. So A and C we would have to mark out. And also they are not independent. So what that means is more people actually play the woodwind. More males play them than females, because notice we have the same number of males, same number of females, so it actually does matter if you're male and play the woodwind, because more of them do than the females. So it is D. And we, again, independent will come up more tomorrow. Number 6, a die is loaded so that the number 6 comes up 3 times as often. So it has to come up 3 times as often, which means the number 5, 4, 3, 2, and 1 just come up 1 time as often. So that adds up to 8. So there's 8 possibilities. So a 6 could come up 3 times, and we want to know what's the probability of rolling a 1 or a 6. So it could come up once, 6 come up 3 times. That's 3 8s plus 1 8 is 4 8. So that's the probability B, 4 8, which goes to 1/2. Number 7, you draw 2 marbles at random. You have 20 marbles. Remember, this is key right here, without replacement. It means when you take a marble out, you do not put it back. So the chance of getting a red marble the first time is 20 out of 50, times the chance of getting a marble the next time is 19 out of 49, because you've taken 1 red marble away, so there's only 19 red marbles left, and you've taken 1 of the total number of marbles there, so there's only 49 left. So the chance of both of those happening, multiply together and get 0.1551. Down here, the probability of A given B. So given that B happens, B has a probability of 0.6, so it goes on the bottom, and then the probability of A and B is 0.1, so that goes on top. Remember, it's probability of A and B over the probability of B. That's our conditional formula. It's on your notes, and so that gives you 1/6. Number 9, we can conclude that either A or B always occurs, and here's why. If you look up here, A occurs 0.5, B occurs 0.6, and they both occur 0.1. So if we were doing the adding and subtracting like we did on Thursday, you do 0.5 plus 0.6 minus 0.1, that actually equals 1, which is 100%. So A or B will always occur, and that's because this equals 1. If you add them up and subtract them both and it would not equal 1, then you could not say that they always occur. And then mutually exclusive means one can't occur at the same time. That wouldn't be true. Independent, we don't know, so that wouldn't be true. And then complementary means that they would add up to 1 each other, and 0.5 and 0.6 doesn't do that, so that's not true either. Number 10, if you buy 1 ticket in the lottery, the probability of winning a prize is 0.11. Now it's saying you play the lottery for 5 months, so the probability of winning is 0.11, probability of losing is 0.89. Okay, so losing for 5 months straight is 0.89 to the 5th power, or 0.89 times 0.89 times 0.89 times 0.89 times 0.89. So 1 minus losing every month will give you the probability of winning at least 1 month. Because here's the probability of losing every month. And so if you do 1 minus that, you will get the probability of winning at least once. And so that probability is 0.44, or 44%. So again, you can look back at this, and you can go back through my work, because all this is going to be on the test. If you notice, this was test 5B. You're going to get like test 5A. So same type of problems. So look back over my video. It'll be posted online. Look back over any notes, take any notes, work through some of these today, and make sure you know how to do them. Now, let's go to the free response you're about to do. On the free response here, the first one is just talking about to comment on the disagreement between a husband says we're bound to have a daughter. He's already had 2 sons, and he thinks we're bound to have a daughter. The wife says it's nonsense. She says that 2 boys in a row means they're more likely to have another boy, and it says to comment on this disagreement. And remember, past experiences and future, so think about it. If the probability that person in the United States is left-handed is about 0.14, what does that actually mean? Think back to where we said the probability of getting 3 of a kind was 1 out of 50. What did that mean? So what does 0.14 actually mean in the law of large numbers? And then setting up Mr. Miller's class, you want to set up a simulation, which means assign some people left-handed, assign the others right-handed, pick a line to start on, and go through and pick 28 pairs and see how many actually turned out to be left-handed. Here is a report of 100 classes of 28 students. What we're looking at is Mr. Miller's had 8, so we're wanting to know how many had 8 or more out of 100, and then what percent is that, and then is that unlikely to happen or not. So like, should Mr. Miller be surprised that he had 8 or more left-handed people, or is that common, or how often does that happen based on our trials? Over here, you want to fill in this probability that would make them add up to 1. You want to go through and answer the next question based on that table. This down here will be a Venn diagram. Remember, there's 20. It says there are 35 students, so you know that your Venn diagram, all the numbers have to add up to 35. Again, start in the middle of a Venn diagram. It says 8 turned in both, so you know you want to start with 8 in the middle when you work through your Venn diagram there. And then part B just asks for an actual number from the Venn diagram. Number 3 gives you the table with all the totals. 2 mutually exclusive events. That means 2 things that cannot happen at the same time. So for instance, you cannot drive a sedan and an SUV. So they're asking them what the car they drove the most was. So they can't drive a sedan the most and also drive an SUV the most. They can't drive a truck the most and also drive a sedan the most. They can't exercise 30 minutes for 4 more times a week and also not exercise 30 minutes for. So pick whatever you want, but remember, mutually exclusive means they can't do both at the same time. But remember, they could drive a sedan and exercise, so those aren't mutually exclusive. I was telling you earlier what is mutually exclusive. Probability that a person selected drives an SUV, so look at SUV out of the total. Probability that they drive either a sedan or a truck, and then probability that they drive a truck or exercise 4 more times per week. That's the both. Remember, probability they drive a truck plus the probability they exercise 4 or more times a week minus the probability that they do both. And that takes you through these free response. And then you should have time, should be about 25 minutes in the textbook. Homework tonight is centered around the Venn diagrams, so make sure I put on there drawing the Venn diagrams. You really want to make sure that you draw the Venn diagrams big enough so you can see it, that you label both circles what they are, that you put all 4 numbers. There should be a number in here, a number here, number here, and then a number in the corner, because that has to be the part that's not this and not this. So remember, there's 4 numbers. All of them, if they're probabilities, they'll all add up to 1. If you're talking about actual numbers, they'll all add up to the total. We practiced that again, but look in your book. A couple of the odd ones should have a little bit of explanation in the back if you need to look at that. But with 25 minutes, you should be able to finish most of those, and not have to have too much going forward. Okay, so I'll be back tomorrow with the next section. Your chapter 6 test is going to be on, you're going to look for that on Wednesday. So basically we went through 10 questions that are these multiple choice that look like the chapter 6 test. We went through some free response questions that look like the test. Tomorrow I'll show you some free response questions that came directly from another version of it, and we'll start off with those for the warm-up instead of multiple choice, and then we'll review. So Wednesday will be chapter 6 test. And you're looking for tomorrow being review, Wednesday the test, Thursday starting chapter 7, Friday continuing chapter 7, and then next week when I'm back, review on Monday, and chapter 7 test will be Tuesday. If you have any field trip forms, permission slips, any of that to turn in, make sure you turn it to Mr. Painter. He'll take them and put them in my desk, and I'll make sure to get them. If you have any questions, just leave it on the discussion board, or leave them on my board at school, as I'll have to come in each day to print off the work. Alright, we'll see you later.